So now we are going to get into the final segment of the material that we are looking at in this course, which is considerations when you want to bring something into a production environment, right? And these are sort of more practical considerations, not directly related to the code itself, but are very important when you actually want to build a product rather than just a prototype. Right? And there are many issues that come in over here. The first and foremost is what's called a secure boot chain. And the reason why this is important is because when you finally go and deploy a product in the field, you yourself need some kind of guarantees that the code that is running over there has not been tampered with, and whoever is using your device should also have the confidence that whatever they got from you is what is actually running over there. Nowadays, we keep hearing in the news about so-called malware and various other kinds of viruses, trojans and so on that could infect various embedded systems, right? Most of the largest botnets that are around today are actually sort of infected routers, right, which in some sense are embedded systems. They're sort of supposed to be just, plug in and forget that they exist kind of devices, but they are running full-blown operating systems. The problem is they have got infected with some kind of code which is running on them and which is being used for malicious purposes. Now, you might also have encountered, for example, something like your Android phone, right, which doesn't easily allow you to make updates. Any updates to the OS have to come from the vendor, and the entire process of sort of changing that is more complicated than, let's say, on a laptop where you want to install Linux. Even on a laptop, nowadays if you want to install Linux, you probably have to go into the BIOS, turn off the secure boot and do a few other things before you can actually get a straightforward implementation of Linux installed, right? So what is done in this scenario is, I would like to make sure at every step of the way that the code that is running on the system is something that I actually wrote. Now, in order to do this, there are the entire, the field of cryptography has come up with this notion of what are called signatures and message authentication codes, right? You might have heard of things like MD5 or the SHA sum, which is used in order to verify that a particular file that you downloaded is actually identical to what was being provided originally by the authors, right? Now, how does that work? The point is that there are ways by which I can look at a particular block of bits, right, a file, and perform what's called a checksum on it, right? Not the small parity checksums that we use in order to detect whether a bit has gone wrong, but something that can actually detect whether anything has changed anywhere in the file with a very high degree of confidence, right? So these kind of checksums can be used by the vendor in order to say, look, this is what I actually programmed into the system, and I want to make sure that this is what is actually running. Now, the tricky part when you are trying to build an embedded system is, where do you start, right? Because remember the boot process, right? We have something called a boot ROM, which in turn loads our first stage bootloader, which in turn loads U-boot, which in turn loads the kernel, which in turn loads the rootfs, which has the actual programs that you are executing, okay? So I have an entire chain of software that's running over here, and at any step of the process, I don't want it to get compromised, right? Now, the way that that's usually done is, I can think of it as, let's say that I have a U-boot, I have somehow verified that the U-boot that's running is correct, and it wants to sort of load a kernel. How does it find the kernel? It basically goes and looks at a particular block of data sitting on a file system somewhere, let's say on an MMC card or an SD card or something like that, right? And what the U-boot can do is, maybe the U-boot internally has some information that says, I expect to see a kernel with this kind of authentication or checksum, right? Maybe a SHA code, right? A SHA-1 or SHA-256 sum corresponding to this particular kernel should be this particular value. Now, that sounds good. It basically says that if I can rely on my U-boot, the U-boot will basically go look at what is there on the SD card. It will first read the file from there, perform a checksum on it, make sure that it matches what it expected, which is there inside the U-boot itself. It's not something that it's reading from the SD card, right? That's the important part. The expected signature has to be inside U-boot, right? And it has to be verified against whatever it actually sees from the kernel. If the two match, then it says, okay, this is a kernel that I trust, that I have been told to trust, load it into memory and get it active. The kernel at that point can basically go and do the same thing for the root file system. It basically says, okay, this is a large root file system, several gigabytes in size. Let me see if I can do some kind of a checksum or some other authentication on it, right? But by doing so, right, which could be a relatively quick process, maybe a few seconds or so, right? I perform some kind of a checksum on the rootfs, maybe it's in some compressed format, and says, okay, this is the SHA that I came up with, and yes, this is what I was told to expect. That was also compiled into the kernel, right? And it says, okay, I trust this rootfs, load it into memory, start executing programs from here. So you see what's happening. The U-boot had some internal information that said, okay, now trust this particular SHA code. It looked for the kernel, found that code and decided to execute it. The kernel then looked at the rootfs and was told to expect a certain SHA code, and it said, okay, I found this, I'm going to go ahead and use it. What about who loaded the U-boot? That was the FSBL. So the FSBL needs to know what would be the code corresponding to U-boot. So far so good. Who loaded the FSBL? That was the boot ROM. Okay. So the boot ROM also has some information that says this is the expected code corresponding to the FSBL. And this is where our problems start, right? Because who's telling the boot ROM what code to expect? And this is where we essentially have some kind of a trust anchor, right? The boot ROM is immutable, meaning that it is literally hardware that is inside the SoC that cannot be modified. It's usually using something called eFuse, the eFuse being some kind of a one-time programmable system. The set of bits over there can be set once but can never be tampered with again, right? It is immutable, it cannot be changed, it is tamper proof, right? Nobody, even with physical access to the system, they cannot change the contents of that. If so, I can actually put a key into the boot ROM, which basically says if the FSBL is signed with that particular key, right? It's not exactly a checksum, that was sort of oversimplifying matters. What it actually says is if this FSBL has been signed with a key, right? And this whole business of RSA, public keys, signing and so on are out of scope of what I can cover over here, but are interesting topics, well worth sort of learning more about, right? Not essential to the practice of actually using an embedded system, but useful to know. So as long as my boot ROM contains this public, contains a sort of, it contains information about a very specific key over here, right? It contains some kind of a signing authority information. What it means is that it can verify that this FSBL was generated by someone who had access to the private key, right? And that effectively sort of tells the boot ROM that this FSBL was generated by somebody trustworthy. Okay. So that's the first stage of the chain of trust that has been established. Once that is done, very good. I have another, just like K0, which was the trust anchor key, I can have another key which is related to the FSBL, which basically says, okay, I have a K1 key which is used in order to sign this. Then I could have a K2 key. From here onwards, it's actually the chain is fairly straightforward. At each point, I program into this what to expect over here, or what kind of key this is going to be signed with, right? And as long as I have trust in this very first step over here, I can sort of chain that forward and say up to here I can guarantee that nobody has tampered with the code that was written. And that's the best that you can really hope for, okay? Now, the interesting thing is, in the context of these FPGA based systems, we have one more what's called an attack vector, one more place where I could potentially change things around, the FPGA bit stream, right? I need to also make sure that the FPGA bit stream itself has been signed and is properly sort of guaranteed by someone. It could be that the FSBL basically uses the same signature based mechanism in order to authenticate this. Usually what is done is something called an HMAC, which is a hash based message authentication code, something which basically says that I know the origin of where this bit stream came from. I know that this code could only have been generated by somebody who had access to things, right. Now there is one more thing that I need to do in the context of an FPGA, right, which is I don't want somebody to be able to just take the bit stream that I have, put it onto their own board and get the whole thing running out there, right, because after all I have invested in developing this board, in getting certain IP running on it, and I don't want it to be such that somebody else can just copy my entire board, put the bit stream over there and get things running. The bit stream itself can be encrypted, and this can be done using a mechanism such that only in a scenario where you have this chain of trust will you even be able to load the bit stream onto the FPGA, right. The exact mechanisms for doing this are dependent on the specific FPGA and the platform that you are using, but the point is that such mechanisms exist. People have thought about it, they do have ways by which they can implement such things. We are not getting into the details of how exactly it's done, but if you are looking at production deployment of a secure chain of code, you need to be aware of these things, as they might be something that you need. You might also choose to go with an alternative thing that your bit stream is not by itself the major problem. If somebody does copy the bit stream, it's okay, your product by itself is what is more important, except that you do not want to, it is something to be aware of. You need to take that as a conscious choice and say that okay, this is not really a primary concern. So ARM processors, among other things, they also have some specific capabilities where they provide secure and non-secure enclaves, or parts of your hardware that literally have access to very specific kinds of code or data, right. There is something called the trust zone, where you can have certain a part of the OS which is called the trusted OS, where there are certain cryptographic keys that are actually stored inside the SoC itself, right. This can be used, for example, to do validation of the secure boot environment, and even potentially for decrypting the bit stream that is being loaded onto the FPGA, right. So the idea is that whoever is manufacturing the processor itself provides these facilities, right. The normal world, as we call it, would be the rest of your operating system, the Linux kernel, the applications, device drivers and so on. The interesting thing is I can actually have a scenario where the drivers that are there in the Linux kernel can actually perform cryptographic operations, right, like encryption, decryption and so on, by calling the secure world, calling functions that basically activate the code that is running over here, without ever having to see the keys that are being used for encryption or decryption, right. So in other words, the keys will be stored safely over here. Even in principle, the code that is running on this side does not get to see what the keys are. It just performs a call to this side to check whether a particular key has been used or whether a particular bit stream can be decrypted, and the results come back from here and are used, right. So by doing this, we can actually enforce one higher level of security. We can basically say that look, it's even more difficult for someone to tamper with the system, because now they literally have to go inside the SoC in order to tamper with these aspects of it, and that's pretty much not possible under normal circumstances.